So I'd like to introduce Huihuo Zheng, who is with Argonne National Laboratory, and talk about the caching wall connector that he's been working on for a while.
Mm-hmm. Okay, hello everyone. So this is one of the recent development in the HDF5 as a scale computing project. So our main concept is to incorporate the non-local storage into the parallel I/O workflows to improve the parallel efficiency. Sorry, my son is making noise. So the motivation is that in many modern HPC platforms, we have not only just the remote storage from the parallel file systems, such as Lustre or GPFS, but also there are the local storage attached to the compute nodes, for example, SSD or NVMe. And so this has become a typical design in modern HPC platforms. For example, in Theta, we have a Lustre parallel file system, and each node is equipped with 128 gigabyte SSD. And in the recent system we deploy called Theta GPU, which is essentially the NVIDIA DGX3 nodes, and each node have 15 terabyte of NVMe local storage. Same thing for Summit, also have non-local storage there. So this is our motivation, is that whether we can use this non-local storage to improve the parallel performance. And there are certain kind of advantage for the non-local storage. First is the local to the compute node. So if the compute node want the data from the non-local storage attached to it, it can just go through the PCIe link. It doesn't have to go through the interconnect. So there's not too much of network contention from the other job of the system. Second thing is that typically the aggregate bandwidth of the non-local storage is higher than the parallel file system. For example, on Theta, we have the peak write bandwidth for Lustre, which is only about 200 gigabyte per second, whereas the aggregate bandwidth for the SSD is 3 terabyte per second, which is one order of magnitude larger than the parallel file system. On Summit, this is 3 times larger than the global parallel file system, GPFS. But however, it is kind of a challenge to use the local storage. First, it's distributed. It is not unified into one piece of storage. So there might be the MPI communication involved if the node wants to access the non-local storage from the remote nodes. Second, in a lot of cases, these local storage is only accessible during the job running. So once the job finished, this space is no longer available, and the data will be cleaned up. So it has kind of, to our best knowledge, is people usually just use non-local storage as a way to store data temporarily. In another sense, is just use that as an extension of the RAM. Say that if you don't have enough storage on the RAM, you can put some data on the non-local storage. But our goal is to incorporate that non-local storage for caching and staging data to improve the parallel performance. And so the talk will basically is about the design of this caching wall, and also I will present some initial performance evaluation. But before do that, I want to say that because of the external pass-through wall connectors, it makes things very easy. So the application can adapt this caching wall without too much code change. So the one thing is that in our caching wall, we have certain part of the I/O work which is done asynchronously. So in order to take advantage of that feature, we'll have to insert some compute work in between the dataset read and dataset close. Same thing for the write case. And also, we also use the background thread to deal with things at current stage of development. So we need the MPI initialization with the MPI thread multiple. I want to emphasize that because we're using the WAL framework, we use the same HDF5 public API, still the dataset creation, write, and close. And it's currently is compatible with H5Py also. So this can be used not only for traditional HPC workloads, but also for Python workloads. And then the second step is to point to the application where the installation of the WAL is. You set the WAL plugin path and also WAL connector to use, and also add that to the LD library path. Then to enable this caching WAL, we provide two options. First is to set these global environmental variables. Basically, this H5, for example, here HDF5 cache read equal to yes means that we will turn on the caching effect for all the read workloads, all the read IO requests. And then we also set the local storage path to tell the application where is the non-local storage located, and also the type of the non-local storage. And the second way is to do it through explicit API controls. We allow the user to set these all the cache WAL related settings in the file access property list. So once this has been set in there, then all the file creation or file opening will turn on this cache fetch. And we also, besides that, we also allow the users to explicitly create a cache for the specific file or specific data set, even if you don't set this file access property list in the beginning while you create the file. So you can still create a cache in the middle of the simulation. The difference between these two options is that the first options is a global setting. So this will set this caching for all the read and write. Whereas the second options, it can set for specific file and data set. But it's kind of very easy to set in both these options. And so now let's look at this, how we design this cache WAL. So as we mentioned that we still use the same API. So for the parallel write case, we still call this H5 dataset write. So in the native dataset write, it's just write data directly from the RAM to the parallel file system. Whereas in our caching WAL, we insert the intermediate storage layer here. Basically, we copy the write buffer into the non-local storage first, and then write it to the parallel file system using background thread. I want to say two things here. One is that this data migration from this non-local storage to parallel file system is done in the background. So it allowed this part of work to overlap with the compute. For example, this without caching, just to compute and then do the data writing from the RAM to the parallel file system and then do another round of compute. Whereas with caching, we can do the compute and then write the data to the non-local storage and then start another round of compute while we are doing the data migration from the non-local storage to parallel file system. And the second thing I want to emphasize is that when we write the data to this non-local storage, we create a memory map files on the non-local storage. So so there's no actual memory consumption here. So if you use the caching WAL for the write case, it won't increase this your memory footprint of the application. So, and then all these details are hidden from the application developers. So the application doesn't need to kind of care too much about how this data migration is done in the background. But those, but it does that this code is kind of semi-synchronous code. So once the dataset write returned, this buffer is already reusable because it's saved that the data is already copied to the non-local storage. So this buffer can be reusable for the later on application, for the later on part of the application. So this is for dataset write. And for the dataset read, we basically have to the idea is to move the data first to the non-local storage, and then later on, when the computer need the data, they just directly fetch data from this non-local storage instead of going to the parallel file systems. And we allow two type of data movement from this parallel file system to the non-local storage. First is we call on-the-fly prefetching the data. So basically, or on-the-fly caching the data. Basically, for example, in the first iteration, when the application read part of the data from the file, it will immediately cache that to the non-local storage using background thread. This is the first approach. The second approach, we also create a H5 prefetch. So this allows us to just prefetch the entire data set at once to the non-local storage before actual read happened. And currently we support both. And then the other key design here I want to emphasize is that, as I mentioned, these non-local storage are detached from each other. They are not connected into a unified piece of storage. So it is kind of challenging to access remote non-local storage. So the way we accomplish this is we use the one-sided MPI communications. So maybe not all of us are familiar with this. So, but the idea is very simple. Basically, each MPI process exposes a part of its memory to the other process, and so the other process can directly read or write to this part of memory without requiring this synchronization of that process. So it kind of reduces the communication overhead by using this one-sided communication. And those also, the second thing that is this one-sided communication works with memory. So in order to, but we want to make it work with the storage. So we also create memory map files and attach the pointer to the MPI window, and then use the one-sided communication functions like MPI put to write the data and MPI get to get the data. So this is the key thing here. So in this in the dataset read, we will first create this memory map buffers and then create an MPI windows, and then we read the data and then do the caching asynchronously. And later on, when we read the data again, we just directly read data from the non-local storage using MPI get. And so essentially, what we have accomplished here is to reduce the I/O overhead from RAM right into from parallel file system to RAM to this non-local storage to RAM. So and we hope that at large scale, typically this is much faster than directly reading data from parallel file system. Then I would like to talk about a lot about the storage space management. Typically in the application, we have multiple files which trying to use this not local storage. So the way we accomplish this, manage this resource is that say that one file want to cache data, it will try to claim a portion of storage from this non-local storage device. And when it's successful, a folder will be created and all the data will be put inside this folder. And another file come in and do the same thing. But now when we have a third file, say that this device already been filled with data, then what it will do is that it will try to free up space and to basically remove the cache, for example, for file 2, and then to fit in the file 3. If the cache has been removed, then the future data access for file 2 will be redirected to the parallel file system instead of going to the non-local storage because the data are no longer there. This is the way we kind of manage this cache space, and we implement several replacement policy like FI, FO, LFU, LRU, which I won't go into detail. And then all the cache will be removed after the dataset close or file close. Then I will briefly show some performance evaluations. This is for the parallel writer case. We do the benchmark on theta and summit. So basically, this orange bar is writing data directly to the parallel file system, and up to 500 nodes, we get about like 10 gigabyte per second for one shared HDF5 file. Whereas writing data to the local storage SSD, we kind of give the linear scaling efficiency, and it reached to about 200 to 300 gigabyte per second, which is one order of magnitude larger than writing data directly to the parallel file system. Same thing for Summit. Here we do the text. We cache the data on RAM, on not local storage like NVMe, and we also support caching data on RAM. For RAM, basically just move data to the memory, do the memory copy, so it is very fast. So writing data directly to the GPFS, we get about bandwidth 200 to 300 gigabyte per second. And if you go to a larger scale, due to the contention from the other job in the system, it actually doesn't improve the performance anymore. But using this non-local storage, because it's not network contentions, it consistently increase the performance, and we get about more than 1 terabyte per second of I/O rate. Then this is for the parallel read benchmark. We kind of, in this benchmark, we try to mimic the deep learning case where we read the data randomly from the file using the data shuffling. So, and then because in our framework, it allows us to get data from remote storage. So we kind of support this data shuffling scenario. So again, we can see that by using this caching, reading data directly from the non-local storage, we can get performance boost from compared to the reading data directly from the global parallel file system, both for Theta and Summit. For Theta, the performance improvement is more significant because the share file performance on Lustre is not very good. So I think this is all I have for the initial performance evaluations. In conclusions, by using this cache wall, we improve this I/O scalability and achieve higher aggregate I/O bandwidth over the direct I/O to the parallel file system. And everything has been implemented in wall framework, so it is very easy for the application to use this framework without too much change of their code. And in future work, currently consider stacking this async wall with the caching wall, so that async wall to take care of all the asynchronous tasks. And we also integrate into other part of the development within the HDF5 projects. And this is the links to the Git repository. If you're interested, you can try, and then let me know if you run into any problems. So with that, I would like to thank the Scale Computing Project and the computing resource from Oak Ridge and Argonne National Lab. And I'm happy to take any question that you have. Thank you very much.
That's great. Thank you, Huihuo. Does anyone have any questions about this work? We've got 30 seconds for a question. So a question in the chat, Huihuo, if you've got it.
Yeah.
The application needs to do some work between write and close to give the vol time to move data. What happens if there's not enough work?
Right. If there's not enough work, then still basically we cannot hide the I/O completely. So there will still be some time showing up in the overall I/O overhead.
Yeah, amazing.
And one thing I forgot is that we at the forgot to mention is that in the at the edge dataset close and dataset file close, we wait for all the I/O tasks to finish. So it is kind of safe if your application terminated successfully without any error. All the data will be guaranteed to move to the parallel file system.
Okay, that's great. Any follow-up questions? If we could take them to the chat or to Huihuo directly, that'd be great, or to the HDF5 vol mailing list.